In this video, we'll optimize the response of the motor with Autotuning in Sigma7 Plus version 7. Hi, I'm Matt Pelletier. Here's a quick preview. We'll disable tuningless on the x-axis, then measure the moment of inertia ratio for the connected load. We'll use the program jog move profile as the position reference, set the mode and mechanism, and execute the auto-tuning sequence, measuring the final response. I'll give you a few troubleshooting tips and then let you try it out on your own with the y-axis. So please follow along and let's run through auto-tuning. To improve the response beyond the capability of tuningless, the next stop is auto-tuning, as long as the load inertia does not change. Autotuning is an algorithm that measures the servo response and iteratively makes tuning parameter adjustments while the machine runs a test move over a number of cycles. It can apply advanced tuning features such as model following control, vibration suppression, and anti-resonance. As usual, I have connection here to the demo, and we'll go to Sigma7 Plus version 7, and let's start with a clean screen here. Close any other windows you may have open in Sigma7 Plus. And you see here we are connected on axis A, that's the x-axis. The first step to get down to the auto-tuning is to go down here to tuning. And the summary of these warnings is simply that the motor will move and won't return to the place it is now. Let's click execute. And by clicking OK, we disable the tuningless function. OK. We need to reboot, cycle power, software reset. So OK. Into the menu, software reset. Execute that, and click execute. Okay, it says we should reconnect. So we come up here to menu, disconnect, and connect again. Now that tuningless is off, we go into tuning again with the same message. And the basic auto-tuning process is outlined right here. We'll start at the top and work our way down toward the bottom. It's very important to know the load-to-motor moment of inertia ratio when tuningless is off and have that set in parameter PN103 because the position loop and speed loop gains are scaled by this parameter. So if you don't set it accurately, you're not going to get a very good tuning result. For this reason, the software provides this feature to measure the moment of inertia ratio, often referred to as JL divided by JM, inertia ratio. But in order to execute that, the motor is going to have to do a little test move. Click execute, and that opens up this condition setting window for the moment of inertia measurement. You don't usually need to change the values on the left, but you do need to pay attention to the reference selection and the speed setting here on the right. Choose a motor RPM that is appropriate for the mechanism. Generally speaking, the higher speed and higher acceleration values will result in a more accurate moment of inertia ratio measurement. Our worst case test move was 3000 RPM, and so this one here at 1000 RPM is definitely within range. You can always confirm with this button, and this gives you the speed and XL decel time. This is the move that's going to happen over a distance of 2.5 rotations. So of course, check that you have appropriate travel distance, and if necessary, you can use these sliders to make any adjustments so that you don't exceed the machine's range of motion. For this demo, we can leave everything at default and click next. This is a function built into the servo, so we click start to transfer those conditions we just set to the servo. Click next again. Now let me adjust the window, and you might want to turn on the speaker so you can hear what's going on. And now we will servo on, execute the move forward, and again reverse. You see what it did here, it iterated starting with an arbitrary value of 3 to 1, 300% load to motor inertia ratio. It did this test move and it comes up with now a closer value of 10 or 11 to 1. We'll do it again, forward. And reverse. And again, forward. It's doing a little test move, and it's running the equations of motor sizing backwards. Torque equals inertia times acceleration. Well, it's measuring the torque, it's measuring the acceleration, and trying to figure out the inertia. Hit reverse. Now we've got about 15, 16 to 1. Again, forward. And it looks like it's settled in on 15.93 to 1, or 1,593%. So follow this here through to the end with next. Turn the servo off. And now we can write this result into the parameter, PN103. Finish this up. We're prompted for software reset, okay. And here they even pop that up for us, software reset. Drive turned back on, software reset's complete, and we're back to the tuning screen with the inertia ratio measured and set. Okay, now we're ready for the next step, which is auto-tuning. You've got two choices here, position reference input and no reference input. Which one do we choose? We'll choose position reference input. The difference is shown in the little picture here, the controller sending a command to the servo or no reference input, which would mean that this function itself can set up its own little test move, similar to what we had here in the moment of inertia ratio measurement. So while program jog is internal to the servo, it's still seen as a position reference input to the control system. So we'll use position reference input to tune to the worst case move that we have set up in program jog. And click auto tuning. This is our final setup screen for auto tuning. We have mode selection and mechanism selection and tuning parameters. The default is mode number 2 for positioning. We'll leave it at that. The mechanism we will change to rigid model, and we will check the box start tuning using the default settings. So why choose mode number 2? Well, there's 3 modes here. Mode number 1, standard, will allow you to have the lowest position error, but not the lowest settling time. If you want the lowest settling time, then you choose mode 2 or mode 3. See, mode number 1 allows you to use notch filter and anti-resonance, but mode number 2 allows you to use model following control and vibration suppression in addition to those two. And mode number 3 is basically the same, but may result in slightly longer position settling time in order to prevent overshooting, meaning that as the motor stops, it won't overshoot the final target position. With mode number 2, the motor may overshoot slightly, but the total position settling time will be the shortest. If you remember back in the overview to tuning, we had said that we wanted to tune the motor on the left and the right to optimize for the lowest possible position settling time, while at the same time keeping the axes synchronized to each other. So it'll be mode 2 for these two axes, and for the z-axis, we said we'd tune for the lowest position error. Now, what about mechanism? We chose rigid model. Why don't we choose belt or ball screw? The simple answer is just choose the model that most closely represents what you have. But what these 3 mechanism selections are about is setting the level of mechanical compliance in your system. Systems with more mechanical compliance, like a belt mechanism, tend to be less stable, whereas this rigid model is very stable and will be capable of a very high frequency response. The setting you choose here balances the bandwidth of the torque, speed, and position loops and helps keep the system stable based on the level of rigidity or mechanical compliance in the system. So that's why we chose rigid model. Finally, you should check the box for start tuning with default settings. The auto-tuning algorithm is optimized for starting with default and finishing fully tuned. Running auto-tuning a second time does not improve the result. However, if you've set some parameters, for example, to eliminate the noise, you may have reduced PN100, you might leave this box unchecked so that it doesn't revert back to default. Okay, it's time for the moment we've all been waiting for. We'll click Next. We'll confirm that we're setting the tuning parameters, only the tuning parameters, back to their default. And click Yes. We confirm the inertia ratio that we just measured. And read what it says here in flashing letters. Turn the servo on. Input the reference from the host controller, which is Program Jog. Then click the Start button. So we need to pull up Program Jog. Okay. I have that same worst case move profile. And we'll do what it says. Turn the servo on. Input the reference means execute motion. Yes. The motor's doing the move. And we click Start Tuning. Yes. You see as it's going through its different phases here, the first thing it does is measure oscillation. See what happens to the motor as it stops. That way auto-tuning can tell if it needs a notch filter or anti-resonance filter or vibration suppression filter, and it will attempt to apply those at any time. And you can hear sometimes as the response of the servo is more aggressive, you'll hear that even audibly. Alright, it'll take a good number of moves, maybe around 100. When the flowchart reads tuning completed, you can finish it. And let's take a trace now and see how much the response has improved. Got the menu, the trace. Let me double check my setup. I'm going to do positioning from the start with high precision trace. Display option settling time, and I think 500 milliseconds will be enough for this. Okay. Start. My auto measurement's giving me a settling time of 2 milliseconds. I hope you're impressed. Let's zoom in and confirm that. Okay, I've got the coin signal right here. Well, it's hard to say. The position reference speed almost looks like it's stopped right on the mark here. Maybe we need to zoom a little more. Yeah, I'd say 2 milliseconds is pushing it. All right, zoom out. Okay, what else we're going to measure? We will measure the maximum position error. It looks like we have from A to B, the difference on channel 3, 1.29 times 10 to the 6. So still quite a high amount of position error, although not as high as it was before. And finally, let's zoom into the torque reference. And let's measure that torque ripple during the move. I would measure it about like this. And I'm seeing about 1%. Now back in our tuning results table, let's make a note of that. We had 0 to 2 milliseconds for the settling time. 1 times 10 to the 6 pulses of position error. And I had 1.1% rated torque ripple. But comparing to the default, we've really brought that position settling time down. The position error is still reasonably high, and the torque ripple is well below 5%. What this means is, while the position error is very high during the move, you see that as the motor decelerates, that error does come down, and we get into the final position at the right time. So the motor's not exactly following the commanded profile, but that's because the most important thing for this method of auto-tuning is that final position and the lowest possible settling time. This is a result of model following control, and we'll see more about that in the next section on custom tuning. All right, I think we can save this result for the trace. I'll call it X Auto Tuning. Save. And let's look now at the parameters that were changed, just out of curiosity. I'll cancel this move. All right. Close all these windows. And look at the parameters. I think this is also a good time to save these parameters to the project. Okay, and save that before we forget. And now, what parameters have been changed from default? Go to function compare with defaults. And we can look at the gain. And this is a good summary of everything that's been changed by auto-tuning. Speed loop gain, position loop gain, moment of inertia ratio. We got some feed forward, we got model following control, tuning less is off. And you can see how these 3 parameters that dictate the bandwidth of the 3 control loops are all on this list. If you want, you could even run those equations, see what the bandwidth is. Don't expect your result to be exactly the same, but it should be relatively close for each of the demos. It is possible that when you run auto-tuning that it will fail. So let's give you a little troubleshooting information on that. The main reason that auto-tuning might fail has to do with that coin signal. The coin signal must go low, meaning it must turn on in between moves. So why might it not turn on? Well, if that positioning completed with parameter PN522 is too low, then if the motor is not tuned very well, it will never turn on. If this happened to you, it's probably because you left PN522 at the default of 7. That means 7 encoder pulses, and that's just not a very realistic position complete for most systems. Another reason it can fail is there's just not enough time between the test moves in program jog. 1 second between moves is usually enough, that's why we used 1 second. But if you do need to tune to a very narrow position completed width, then you might even want to set up the program jog with even more time between moves, maybe even up to 10 seconds, just to be sure that that coin signal will indeed turn on. Keep in mind also that auto-tuning maximizes the system response, but it looks also for stability of this coin signal after the move is complete. If the coin signal turns on and off, the auto-tuning will reduce the response of the entire system until that doesn't happen anymore. Therefore, a smaller value of PN522 position completed width will result in an auto-tuning response that is lower. And another reason that's not listed here that auto-tuning may fail is due to a mechanical problem. If you're hearing a lot of noise or just auto-tuning is not working for you, please give us a call here at YASKAWA or send us an email, and we'll check to see that there's not any mechanical problems with the demo. Please keep these troubleshooting tips in mind as now you auto-tune the Y-axis just like we did the X-axis. And record your measurements for the auto-tuning of this axis. It's essentially the same motor and the same load as the X-axis, but do you think the auto-tuning result will be the same? Now, just a couple tips before you get started. Remember to select axis B every time you open the menu. And let me show you, you have to set up the trace a little bit differently. So for axis B, you click on the menu, always select axis B, but now when you choose trace, go into your setup, and you need to set the measurement axis to select axis B and only axis B. If you select both axis A and B, then the trigger will be looking for motion on axis A. You could manually change that, but it's just as easy. Just uncheck axis A, and now axis B becomes the trigger. The rest of the setup is the same. So please pause the video and go through auto-tuning on your own. If you run into trouble, I would recommend you compare the parameters between axis A and axis B in Sigma7 Plus. And the remainder of this video, I'll run through the process myself very quickly. And at the end of the video, I'll show you how to get both of the motors moving at the same time and how to graph that. Alright, I'm going to quickly run through auto-tuning on what we're calling the Y-axis, connected as axis B of the SGT7W dual axis amplifier. First thing is to look at those PN500 parameters. Check that my position deviation overflow alarm has 3 zeros at the end of it. And as long as I'm here, I'll also change the position completed width to match axis A, 4660. That's 1/10 of a degree. And write those in. Now we'll go to the menu, click on axis B, and go to tuning, execute. First step, turn off tuning list, okay. Got to reboot. So okay, close this menu. Not going to save anything yet. Again, axis B. And software reset here under setup. Execute that. There's the amplifier turning off and back on. Go to auto tuning again. Axis B, tuning. Execute. The first step is measure the moment of inertia. So execute that one. Leave everything at default like we did on the X-axis. Start this. Click next. Servo on. Forward move. Reverse move. Do it again. And again. One more time. Reverse. And I think this will be the last time. Forward. The last time reverse. Final inertia 1635. It's detecting a little bit more than the other axis, but that's okay. Okay, moving on. Write that parameter in and finish. Gotta do another reboot. Okay. Drive's turning off and back on. That reboot's done. We can now go on to auto tuning. I'll do mode number 2 for positioning. The mechanism is rigid model. And we check start from default. Confirm the default. Confirm the inertia. And now we need to start a move. For that we used program jog. Axis B, program jog. Okay. I'll use the same move as the other axis. 16777, 2160 at 3000 RPM, 35 milliseconds, 1 second, 0 for infinite. Looks the same. And we'll run this. Servo on. Execute. Confirm. All right. We're moving. And start tuning. Yes. Oscillation level measurement complete. Gain search takes a while. And tuning is completed. So finish. Let's take a graph. Axis B, trace, go to the setup. We will select only axis B. It says measurement axis B. I'm going to do position from the start, set, high precision trace, 1000 sampling time, so we have a half a second. Got the display option checked also. Okay, start. And I'll cancel this move. Okay. Alright, let's measure the move. Settling time 2 milliseconds. I'll zoom in and verify that. Cursors show more like 0, unless you count this little bit here. Well, even that, 2 milliseconds is like this far. I'm going to say 0. So same settling time as the x-axis. Somewhere between 0 and 2, depending on how you measure it. Now the position error is horizontal cursor. Put A at 0. Put B at max. Got 1.22 times 10 to the 6. And zoom in a little more for the torque ripple. Zoom a little more. Torque ripple I'd put at about 1.9. So we had 0 to 2 milliseconds here. I said 1.22 times 10 to the 6th pulses. Torque ripple was higher on this motor, 1.9% rated. So now as a little bonus, I said I'd show you how to get both of these motors moving together at the same time. The way I'm going to do that is to use the command from the controller. There's a built-in functionality of the remote I/O. So you need a remote I/O connected for this. And the first thing we need to do here is reconnect the controller over Mechatrolink 3. So go ahead and click on Reboot Controller and Servos. You know that works when the display goes out here. Alright, that went out. Also, you see like a little lowercase c at the beginning of the reboot cycle of the controller. And that takes a good 30 seconds to reboot the controller. Alright, when you're up, you should see no alarm on all 3 axes, and then set the speed to 18,000. Like you see here, that's 3,000 RPM on the Z-axis. And what will happen here, if you turn the servos on and jog the Z-axis, just hold down that button. You see that it's doing a move, and it's a very similar move to what we had just tuned. So it seems like the dwell time is a lot less. Okay, so that's how we get both of the motors to move the same move at the same time. Now let's see how that looks if we graph both. Under the setup, be sure you have the measurement axis A and B selected. Click OK, and start. Now produce that motion. Okay, I think that's enough. It says transferring data. Actually looks like it's giving me the falling edge. Let me try my setup again. We had positioning from the start, high precision trace, 1000, both axes, trigger on axis A. Let's trigger only on trigger A, rising edge of position reference speed. Click start again. Jog away. Okay, and there's the move. Looks like the distance is less, but we still made it up to 3,000 RPM commanded speed. So now I can zoom in here, and you see the two traces. There's also this measurement axis tab now where you can look at one or the other. You can see that they're both pretty much the same in this case. I did it before and they weren't quite the same, particularly the position error. Yeah, you zoom in a little bit, you can see the position error is not quite the same between the two axes, which would imply that they're not quite synchronized if they don't have the same position error. It's off by 3 times 10 to the 4 pulses. So that could be significant. And I'll go through in the next video how to even these out by setting the model following control gain equal. In fact, you can look at the parameter differences between these. Just pull up the parameter list and look at the gain parameters. You see we have slightly different values for speed loop gain, integral time constant, position loop gain. All the tuning parameters here are slightly different between the two axes. And down at the bottom, this model following control gain is significantly different. And that's the reason why they have different position error. If I were to just set this to 6092, let's try that out real quick. Now take a new graph. The trace, hit start. Jog that master. Okay, got something. Now if I zoom in, almost looks like one. Can't really tell the difference. You really got to zoom. And you can see those two are right on top of each other. The position error is not 0, but between the two axes, it is essentially the same. And we'll see in the next video on custom tuning how we might be able to reduce the error even further by playing with these parameters here using the custom tuning interface. Thank you for watching this video. For more information on Sigma7, please go to yaskawa.com. Products, Sigma7 Servo Products.